So you missed the part where I said I'm probably going to grade the first pages of your quizzes today, which might like screw up your grades. Like it might just come through as like half the points until I grade the second page. So later
So we're all
today,
gonna have like 50%.
yes.
Got it.
Wait, so what would the max be?
So the max points of the first page is 20 points.
Okay.
So if you have a 20 out of 50 at the end of the day today, it means you are currently batting 100%. Okay, glad we got that out of the way. So let's go ahead and fire up those notebooks. We're going to look at inverse functions today. What? Seems kind of a basic topic. Share screen. A little bit off my game this morning. The past probably 5 or 6 days, the baby has actually just been sleeping until the time I have to leave. So I have been like actually feeding her. I just kind of grab her out of the bassinet and sit with her until it's time to leave or put her in the car seat. But today she actually woke up and I had to feed her, which makes for a little bit of a more clustered morning. Then she peed all over herself. So that was a curveball. She hadn't done that in a while where I was changing her and then all of a sudden she started peeing and then it gets all over her onesie. And yeah, it was no bueno. That's a good way to put it. That's what babies do. They eat and sleep and pee and poop. Okay, so chapter 5. What? This year is flying by. We're getting pretty close to the territory where last year, for all intents and purposes, ended. You know, the whole Rona thing. Getting my first shot tonight. That's exciting. Yeah. Start living recklessly after this. It's not plugged in? What is going on? It's not.
Wait, could we have done the integrals by hand, or did you want them all in decimal?
If you did them by hand, that's fine.
Okay, cool.
Yeah. I mean, to be totally frank, I'm basically just gonna be looking at the integral. Like, I know what the integral should be. I'm gonna look and see if you got that. If you somehow fumbled from writing the integral to punch it into your calculator, it might cost you half a point or something. But the whole test was seeing your setup. Okay, so this is 5.1. 5.1 inverse functions. Oh yeah. Right, I think it's technically called the inverse of a function. The inverse of a function. So before we dive too deeply into like where the calculus picks up with inverses, I think it's worth our time to spend a minute or 3 or 5 just talking / thinking about what it means to be an inverse and why the method that you might have in your brain to find the inverse of some arbitrary function is like maybe a little unsatisfying, or at least it's a little unsatisfying for my brain. And maybe an alternate way that we can think about this process of finding the inverse of a function. So to do that, we're going to do an illustration. I think this is in the book, but I know that I did go a little bit off trail from the book. Well, I think this function is in the book. I don't know if they quite explain it like this. And so if we had some arbitrary function, maybe some linear function, 4x minus 3. And we know, at least in our pre-algebra days, before we knew what a function was, we could have just said that this was y equals 4x minus 3. That the value of y is going to depend upon what x is and the stuff that we do to x. And if you were asked what is f inverse of x, which we always have to train our brains to realize, okay, that's not f to the negative first power, that's the inverse of f. You probably at some point in your lives, maybe in algebra 2, we're told, okay, well, if you want to do that, which might have even been algebra 1, I don't remember. Nah, probably not algebra 1. Was switch x and y, switch variables, and solve for y. And you're kind of like maybe giving some rationale, like, well, because like they are like the inverses are like flipped over the y equals x line, and yeah, you just flip them, and to me it's kind of gimmicky, but it would look like this: y equals 4x minus 3 is what we're starting with. And so if we wanted the inverse, we were told, hey, switch those variables, make this x equals 4y minus 3, and then solve for y. And we're like, okay, we know how to do that. This becomes 4y equals x plus 3, and this becomes y is equal to x plus 3 divided by 4. And this is what the inverse of f would be. And we'll get into how we would confirm that. But you're like, okay, yeah, I switched to my solve. That's the inverse. Cool. And again, the idea is like, okay, why does this work? And this is kind of what I want to put some pressure on, is why does this work, and is there a better way to think about it? And there's like something about inverses switching domain and range or something. I literally wrote in my notes last year, yada, yada. Okay. So if it's not coming across, I'm not wild about this method in terms of the intuition that drives it, because I don't think the intuition is that clear. And so we're going to kind of introduce a different way. And if you decide that the way that I'm describing in the next couple minutes doesn't make sense, then just go back to this. No harm, no foul. Doesn't matter to me. But the kind of calculus intuitive way and wherever possible, we'd like to use intuition. What does f of x actually do? Well, it tells us how to take one thing, x, and turn it into another thing, y. Okay, through two very specific steps. Multiply by 4, subtract 3. Okay. If we come at this problem then with the understanding that the inverse needs to undo this thing f of x, needs to undo these very specific things that are being done to x, it opens us up to a different way of getting to that inverse function, this undoing function. Okay. So f of x equals 4x minus 3 tells us how to take an x value and get a y value. what we want some function that we'll call f inverse of y. We'll come back to that in a minute. Which takes that y value and undoes the work of f. And ultimately gives us back the original x value. I know this is maybe a little wordy. We want something that's going to undo the stuff that we just did to x. So to me, maybe instead of that magic switcheroo, how about we just solve for x? F is telling us to do certain things to x. Let's see what happens when we undo them. What do we get? So y equals 4x minus 3. Add 3 to both sides, we get y plus 3 equals 4x. Dividing both sides by 4, we get x equals y plus 3 divided by 4. Look, pretty close to what we got up here, but the variables are different. The question is, do the variables matter? Not really, okay? Our choice of independent and dependent variables, independent and dependent variables is kind of just what we choose. We could call this A and B, D and C. This describes a relationship between two things. Do this stuff to this thing and you end up with X. And so this means we can just say that this is whatever we want. So because your choice of an independent variable is arbitrary, we can write the above as f inverse of x is equal to x plus 3 divided by 4, where we do need to note that x is in the range of f. That might seem like kind of a slight point, but to me, it puts your brain in the right frame of mind of what do inverses actually do? Okay. Well, this starting function multiplied by 4, subtracted 3, it makes sense that the inverse of that function is going to add 3 and divide by 4. It perfectly undoes the things that are being done to our dependent variable. And so if we just go through the process of undoing those things, we end up at the inverse. And then with this just slight shift in our brains, understanding that x, y, a, b, theta, zeta, doesn't matter what we use here, we can call this what we want. Okay. Which then brings us to the formal, stuffy definition of the inverse of a function. There is some stuff in 5.1 that I am going to sort of assume prior knowledge on in terms of the horizontal line test and one-to-one functions. If those words don't mean anything to you, you should probably go read the first page or two of this section. Okay? Because that's where our definition of inverse functions begins, with one-to-one. So the condition here is that if f, some function, is one-to-one, which the poor man's version of one-to-one means passes the HLT, but what? The horizontal line test. Okay. Meaning every range value has just one domain value, which is a stricter definition than the one we have for a function. For a function, every domain value is restricted to one range value. Okay, but what a one-to-one function says is there's no repeated range values. That wherever you are, you know that that function value is going to be unique. There's no other place where that function value is repeated. It's like a parabola, not one-to-one. That is the set. So if f is one-to-one, and is also the set of ordered pairs x, y, that is the set of ordered pairs x, y. Then there is a function f inverse called the inverse of f, that is the set of ordered pairs y comma x. As I'm thinking about this, I feel like this is the exact way of thinking about this that I don't like. Well, defined by freaking light hold x equal to f inverse of y if and only if y is equal to f of x. And the domain of f inverse, the domain of f inverse is the range of f, and the range of F inverse is the domain of F. Which is a very long-winded way of saying these things undo each other. Okay, this right here means take some function value given to us by F, multiply x by 4 and then subtract 3 and get that value. The inverse is going to take that value and undo all that stuff and give you back x. Okay? It is an undoing reversal process. And that gives us the how do we check inverses. Okay? And this is something that, again, should be pretty firmly lodged in your brains from Algebra 2 and pre-calc. So this leads to the Algebra 2 pre-calc checking notion. How do we check these things? Well, by understanding that inverses are inverses of each other. Seems kind of obvious, but needs to be stated. This is 5.1.4 theorem. Inverses are inverses of each other. So what? Inverses undo each other. How far are we going to go today? Yeah, we'll get there. So if f is a one-to-one function, having f inverse as its inverse, then f inverse itself is also one-to-one. Having f as its inverse. Furthermore, not every day you get a furthermore in the middle of a theorem. Furthermore, therefore. We have this relationship between the two functions, that if you were to apply the inverse of f to f, it spits you out x. It undoes the work that f does to x, and you end up with x again. So long as x is in the domain of f, and a similar statement can be made that if you apply f to its inverse, the inverse does some work to x, and then f takes it and undoes it. And we get x back out. Again, though, for x in the domain of f inverse, or you could say in the range of f. So back to our original function, we can check this. using this theorem. Do the two functions that we came up with undo each other? So we claimed that the inverse was equal to y plus 3 divided by 4. For y equals 4x plus 3. Okay, this was the like, hey, let's just solve for x method. And so informally, we could just plug that back in. This is kind of like the, well, what happens if we plug y back into this? Does y plus 3 divided by 4 actually undo 4x plus 3? Plug in 4x plus 3, test it out. Sorry, that should be 4x minus 3, right? Yes, 4x minus 3. 4x minus 3. Oh, 4x minus 3 plus 3 is like 4x divided by 4 is like x. Seems to work. Okay, but that's not really a formal, rigorous way to do that. And so we'll use 5.1.4 to show that more rigorously. Rigorously? Put you in the right spot? Yeah, sure. Where we're actually going to define two functions. Here we're just like, oh, here's like the relationship, here's an equation. But let's actually do the functions. That if f of x is this 4x minus 3 function, we can let f inverse of x be equal to x plus 3 divided by 4. And then we verify both of these furthermore statements, that applying the inverse to f gives you back x, and then applying f to its inverse does the same thing. So it seems like a little bit of a repetitive process, because it is, but it's necessary in order to show that it works in both directions. I guess I'd have to think about this, but conceivably, I guess you could have it work in one direction but not the other, which is why we do both. But I can't really off the top of my head think of something. So we'll check the first statement. If we apply f inverse to f of x, what happens? Well, this means f inverse of 4x minus 3 f inverse was x plus 3 divided by 4. So we have 4x minus 3 plus 3 divided by 4. This is kind of similar to the informal check that we did. So we get 4x divided by 4. We get x. So this is half that applying the inverse to f of x spits back out x. We also need to do that in the other direction. What happens if we apply f to its inverse? In other words, put x plus 3 divided by 4 into f. Well, f was 4x minus 3. This would be 4 times x plus 3 divided by 4 minus 3. The 4s will cancel here, leaving us with x plus 3 minus 3. And oh, happy day. We get x. And so this confirms that f of f inverse of x also gives us x. So nothing groundbreakingly new here, but maybe just a slightly shifted way of thinking about the inverse. But in a nutshell, inverses undo each other. We're going to do one more example where we'll compute an inverse and then verify. And then your homework tonight, or it won't be due till next week, but the homework that you'll be able to start tonight will just be finding inverses. And then tomorrow we'll see the rest of 5.1, which will introduce inverses and derivatives. Oh yeah. And that's really where the rest of this chapter will go. Whew. Good stuff on a Thursday morning. Okay, one more example, and then we'll get you out of here, or get you started. Ejemplo numero cuatro. Example number 4. So f of x is going to be the function defined by dos equis plus, I don't know how to say plus, dos equis y tres diviso a equis menos uno. That's our function. Find and verify f inverse of x. I'm going to use the kind of slightly different method where we're going to say, okay, we know that this is equal to y, or some independent variable. It doesn't need to be y, it could be z, it could be s, it could be r, it could be t, it could be star, it could be anything you want. You're in charge. But for the sake of tradition, we're going to call it y. So we're going to say that y is the value that we get when you take x, multiply by 2, add 3, and then divide by that same x minus 1. And so we want to undo all that stuff. It's a little more involved than 4x minus 3. We can still do it. Just need to solve for x. We need to get to the bottom of undoing all the x stuff and seeing what that gives us. So first step will be to multiply both sides by x minus 1 is now equal to 2x plus 3. We're then going to distribute that y, get x times y minus y is equal to 2x plus 3, sorry. I'm going to do two things at once here. I'm going to pull this x over, and I'm going to add that y over. So we end up with xy minus 2x is equal to y plus 3. I added the y, subtracted the 2x. And now I can factor out an x here. X times y minus 2 is equal to y plus 3. And then dividing both sides by y minus 2. We get that to undo all the stuff to x, we need to do y plus 3 divided by y minus 2. And so we would call this some f of y here. Okay. Plug in y, you get this x. But this is only true if that's the inverse. And this is where we make the swap and say that this is the inverse, where we can define these variables however we want. Inverse of f is going to be equal to x plus 3 divided by x minus 2. So at the bottom of it, the whole variable swapping thing and that whole first page of notes kind of comes down to an issue of timing, whether you do it at the beginning or at the end. But to me, the swap at the end makes more sense in light of what we're actually doing here. We're undoing all this stuff that's happening to x, and then at the end just saying, well, we just want to call this a function with our own variables. Kind of a minor point. But then we need to verify, and on your homework you will be asked to do this, and you're probably going to roll your eyes. Oh, this is kind of tedious. But yeah, sometimes that's what math is, tedious. Sometimes that's what life is, tedious. Let me tell you, kiddos, life's hard, and then you die. Live accordingly. Okay. So F. Have I not dropped that one on you guys yet this year? It's one of my go-tos. Anytime somebody complains, let me tell you, life's hard, and then you die. So I guess keep complaining. So we're going to plug in the 2x plus 3 divided by x minus 1 into f inverse. Do we have to? You don't have to, but you should, because I'm telling you to. That's going to look like plugging this into that. Okay, so that becomes 2x plus 3 divided by x minus 1 plus 3 divided by 2x plus 3 over x minus 1 minus 2. Now I really need you to resist the urge to do something stupendously stupid and just cross those out. And you'd be surprised how many kids I've seen do that in a calculus room. This is not -3/2, okay? That's not how cancellation works. We're going to have to do the difficult work of getting rid of these two improper fractions. Okay, so to me, there are a number of ways you can do this. I'm going to clear it out by multiplying top and bottom by x minus 1. So really, I'm multiplying by 1 here. That's a very funky looking 1, but I promise you x minus 1 divided by x minus 1 is just 1. The result of which on the top is this just becomes 2x plus 3. I'll just show it. This becomes 3 times x minus 1. In the denominator, we get 2x plus 3 minus 2 times x minus 1. And we're not feeling like super great here. Just like, yeah, that's really going to simplify to x. Let's see. So we get 2x plus 3 plus 3x minus 3, distributing, divided by 2x plus 3 minus 2x plus 2, -2 times -1. better start canceling out pretty soon. So how many x's do we have up top? We've got 5 x's, 2 x's, and 3 x's make 5 x's. Oh, look at that. We got a positive 3 and a negative 3. That makes nothing. That makes me kind of happy. Down here, we have 2 x's and negative 2 x's. That's no x's. Oh, that's good. And then we have a positive 3 and a positive 2. Oh, happy day. 5x divided by 5. That's x. Therefore, we have confirmed that if you apply the inverse of f to f, you get back out x. But of course, that's only half the story. Really? Yep. We also need to confirm that if we take f and apply it to its inverse, a similar story will emerge. In other words, if we take x plus 3 divided by x minus 2 and use that as an input of f, f should be the undoing thing to this function that will give you back out x. So we check it. We do 2. So 2x plus 3 over x minus 1 is what f was, or is. We do 2 times x plus 3 over x minus 2 plus 3 divided by, well, x minus 1, but we're plugging in this whole dealio for x. So x plus 3 divided by x minus 2 minus 1. So we're in kind of a similar awkward situation here where we've got fractions on top of fractions on top of fractions. So I'm going to do a similar move here where I'm going to clear out these fractions by multiplying by 1. Very specific 1, but 1 nonetheless. So looking at the numerator first, multiply everything in here by x minus 2. We end up with 2 times x plus 3. The x minus 2 cancels with the x minus 2. Plus 3 times x minus 2. Down below, the x minus 2 cancels with this 1 over x minus 2 to give us x plus 3 minus 1. Sorry, minus 1 times x minus 2. And then we go simplifying and hope that we find an x at the end. Distributing twice up top, we get twice x plus 6 plus thrice x minus 6. Didn't think you were going to hear the word thrice today, did you? X plus 3 minus x plus 2 on the bottom. Our spidey senses are tingling, and we think this is going to work out just fine. Because up top, those 6's go away. We're left with 2 x's and 3 x's, which most days of the week will give you 5 x's. Down below, the x's go away, and we're left with 3 and 2, which gives us 5. And oh, happy day, 5x divided by 5 is x. And we have confirmation that indeed, apply f to f inverse, and you're going to get back out x. Woo!
Is there a shorter way to do this, or?
Nah.
No.
Nah. In it for the long haul. What I say, life's hard, then you die. Yep. On our test homework, do you want us to check it both ways? Heck yeah, I do. It's good for you. Okay. Do I need to do this last theorem? Is this important, or is this just Yeah, so we've got time. There's one last theorem that we're gonna just write down because it's in here. Yeah. So 5.1, this is two theorems in one. So we're getting 2 for the price of 1. So that's nice. This is 5 and 6. And we're gonna call these inverse, and this truly is the last thing, and then we'll be done. Inverse function theorems. And basically, these theorems just tell us that inverses are very similar, that they share a lot of qualities. Okay? And so the reason that I put this into one is I don't feel like we need to say this twice. But basically, suppose that that the function f is continuous and either always increasing or always decreasing on a closed interval from A to B. And that is actually a condition for a function to have an inverse. It's got to be monotonic. And that's part of the first page or two that you might want to read if inverses are sort of hazy to you. That a function has to always be increasing or decreasing to have an inverse. Otherwise, if you just think about it, if it ever takes a dip, it's going to hit another range value again. It's going to fail the horizontal line test unless it's always increasing or always decreasing. And so what this theorem is going to say is that whatever quality, whatever monotonic quantity the function has, whether increasing or decreasing, the inverse is going to share that quality. Okay. So first, it's going to say that, well, because you're always increasing or decreasing on that interval, you are one-to-one and you have an inverse. So f has an inverse is the first condition or the first result. Called f inverse. And it's defined on the range of that interval. So defined on f of A to f of B. And then the second result is that it shares the monotonic quantity of f. So if f is increasing, so is f inverse. If f is decreasing, so is f inverse. And finally, the continuity is shared as well. That we can guarantee the continuity of f inverse on its domain. Okay. And just sort of like, I don't know if that last point was made very clear about the monotonic nature of functions that are invertible. If you've got some curve and you're increasing, 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 but then suddenly you decrease, at that moment, this is no longer one-to-one because now there are two of the same range values. it fails the horizontal line test, it's not invertible. Same thing the other direction. If you're decreasing, 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 and then you increase, you're going to fail the horizontal line test. You can no longer find an inverse here. What this function does is, or what this theorem says is, okay, well, that's true. And also, the inverses are going to share whatever increasing or decreasing characteristic the original function has. And that'll come into play later on. Okay, so let's see what you guys can tackle on the homework. Won't be due till Tuesday. We need to finish this. I'm going to give you the whole assignment right now, and then I'll look at the book and see what you can actually maybe do tonight with your last 10 minutes of class. So 5.1 is on page 437 to 439. I will try to remember, actually I'll put it on my to-do list to post the assignment sheet to Canvas. Thursday, wow, Thursday. Flying right along. Post, calc. Yeah, can't abbreviate it that way. I'm gonna write that whole word. Post calc assignment sheet. There you go. It's on my to-do list. But here's the first assignment. It's gonna be numbers 1, 7b, 9b, 13b, 23, 25a, 27a, 29a. Why are there so many letters in this assignment? 41, 51, B and C, 54, uh-oh, getting high, getting to the high numbers, we don't like those, 63, and 65. Oh, and you can't see that because, okay, so let me take a little looky-loo at La Libra, El Libro, really bad Spanish. And see what you can conceivably attempt esta noche. One, yeah. 7, yeah. 9, yeah. 13, yeah. 23, no. So 23 is where we're going to kick off tomorrow. So basically, if you sitting around on a Thursday night or sitting around in the last 5 minutes of class and want to start, you can do these quattro. Those 4. Right. Questions, thoughts, feelings? Well, that's about all I got. So